Hello, and thank you for coming to my talk wherever you might be. My name is Michael Houle, and I'll be presenting today Local Intrinsic Dimensionality 3, Density and Similarity. In statistical modeling with continuous distributions, we typically model things in terms of a probability density function, which I'm sure most, if not all of you, are familiar with. Not all distributions, as it turns out, can be expressed using a single probability density function. The most well-known example is that of mixtures of distributions of different dimensionalities. So we might have a combination of a distribution that's in one dimension, then another that's aligned in a subspace of another dimension, and then some probability weighting is given at the time of generation for deciding which of these distributions generates the observation. But to unify all this under a single PDF, it's possible only when the dimensionalities are identical. So to see why a probability density function requires a fixed notion of dimensionality, consider these three examples here, which are the unit interval in one dimension, the unit square in 2D, and the unit cube in 3D. So imagine now that we have a probability density function which was formulated for 2 dimensions. So as in the middle example with the unit square. So if in the unit square we have a uniform distribution, then doing a double integration of the probability density function, which is just 1 in this case, should give us the total probability of landing in the unit square, which is 1. But if we look at the example in the 1D case, if we try to use this 2-dimensional formulation, we would find that by doing the single integration of something which is set up for a double integral leaves us with an infinitesimal in the y direction, which then, of course, gives us a value of 0. And in the 3-dimensional example on the right-hand side, doing a triple integral of this 2D PDF gives us, we would have to insert the third infinitesimal for the z direction, and then divide that back out again, gives us a result of 1 over d of the infinitesimal in z, which tends to infinity. So this means that in modeling, dimensionality is usually fixed. And when the dimensionality is fixed, we inherit dimensional bias when the intrinsic dimensionality is allowed to vary from one locality to another. These issues can greatly affect, in a negative way, probability density estimation. But it turns out we can do a bit better when we are only interested in the ratio of 2 probability densities. When we have a density ratio estimation, it typically arises in situations where you don't care too much about the absolute density of a particular location, but you want to know whether it is more dense or less dense than some other reference location. So taking the ratio of these two things, if the ratio is 1, that means the densities are the same. Above 1 or below 1 indicates a deviation. So the ratio of 2 probability densities is a unitless quantity in that there is no implicit dependence on any fixed dimensionality there. And so as an example of this would be the KL divergence between 2 distributions, which is a form of entropy, but taken relative to the PDF of some baseline or reference distribution here in this example, Q. Density ratios then are local quantities that may not have units involving the dimensionality, but their constituents, the 2 PDFs that are forming this ratio, themselves need to be declared in terms of a fixed dimensional model. And so the question to be addressed in this talk is there a way around this? So in this paper, this presentation, we propose a neighborhood-based alternative. And that is to consider relative density as a ratio of neighborhood probabilities. So imagine that we have, for a location of interest, let's say 2 locations of interest, x and y for this example, that we consider the probability masses associated with a ball of radius r centered at x and another ball of radius r centered at y. And then we denote by fxr and fyr the amount of probability measure captured by these balls. So here, volumes are parameterized only by the radii, unlike in the case where we have full dimensional fixed dimensional representations, we don't have these multidimensional integrals to deal with in our model. Here we recognize only a single scalar value, which is the value of the distance from the point of interest. And the volumes here in this case are spheres with respect to our distance measure centered at these points. So because we are parameterizing the volumes this way, the underlying dimensionalities are not assumed. It's not explicitly there as part of the model. So one way of looking at these functions fxr and fyr, we can view them as the cumulative distribution functions of distances from x and from y induced by whatever global distributions are generating the data for us. In terms of this, the density ratio is just a limit of the ratio of these CDFs as the radius shrinks to 0. Okay, so the objectives then for the talk are a theoretical analysis of these radial density ratios. And they're motivated as the limit of ratios of CDFs of distance distributions of the form that we've just discussed. But in the paper and even in the presentation, we'll give a slightly more general treatment where we assume that these functions are non-negative, that they hit 0 at exactly 0, and that they have certain smoothness properties near 0. The analysis uses a theory of local intrinsic dimensionality that was proposed 3 years ago by me at SISAP, which has its roots in extreme value theory. And the goal is to show how this LID model these LID quantities naturally reveal themselves when density ratios are modeled this way. So now just a review of local intrinsic dimensionality to start. So we have a motivating example from m-dimensional Euclidean space. If we take two balls of differing radii r, r1 and r2, and we happen to have some machine that could measure volume for us in this Euclidean space, if we knew the two volumes of the balls and we knew the two radii, then we can calculate the dimension that we happen to be in if it happened to be unknown to us. If somebody gave us these 4 measurements, we could deduce the 5th one as just the ln of the ratio of the volumes over the log of the ratio of the distances. For the local intrinsic dimensionality model, we adjust things a little bit by, instead of considering some volume with respect to some unknown dimensional representation, we associate with these balls the probability of some random variable, some non-negatively valued random variable is less than the threshold r. And we assume as our smoothness condition that f is continuously differentiable over ranges of interest. So then in terms of these concepts, the local intrinsic dimensionality is just given as the ratio of the logarithm of these two volumes, now denoted by probabilities, over the ratio of the logarithm of the distances. But here we take as the two radii of interest, the inner ball have radius r and the outer ball of radius 1 plus epsilon times r for some small epsilon. And then we let epsilon tend towards 0 to get an instantaneous measure at r of what this quantity is. So whenever the limit exists, we say that this intrinsic dimensionality exists. And this is related to another notion of the discriminability or indiscriminability of the distance measure, which is taken as the ratio of the relative increase in probability between r and 1 plus epsilon times r and the relative increase in the distance itself. And what was shown in the 2017 paper was that these two notions are the same. That when you take these two limits, which you can solve using L'Hopital's rule, you get a nice compact form. So whichever way you arrive at this spot, this function IDFR begs the question, which value of r should we be using? What distances should we be considering this function at? And if we think of things as in terms of an asymptotic tendencies, well, we know that, for example, using a k-nearest neighbor method, if k is fixed if you're interested in 10 neighbors or 100 neighbors, but you let your sample size n tend towards infinity, that drives the neighborhood radius to 0. So we're interested as a limit effect, in an asymptotic effect, of seeing what happens when these quantities tend to 0. So by taking the limit of these IDs as the distance tends towards 0, we get something which, used in the notation, is just IDF star. And we can refer to IDF star simply as the intrinsic dimensionality, and when it's important to consider some distance other than 0, we can call this an indiscriminability at distance r. So we can account for the local intrinsic dimensionality using an ID representation theorem. So this is the formal statement of the theorem. Basically, it says that if we have two distances of interest, f of r and f of w, that the ratio of these two things is equal to the ratio of the distances themselves taken to the power of the intrinsic dimensionality times an adjustment factor. And that adjustment factor, g of f, as messy as it is, you can show that when r and w are allowed to tend to 0 together, without any one of them being more than a constant larger than the other, by maintaining these conditions, as long as f satisfies the smoothness conditions, then the factor gf vanishes. It tends to 1, and then it leaves us with just a relationship. So we can read this relationship very much in the same way as our motivating example. We have a ratio of fr to fw, which is like a ratio of two volumes, basically is roughly the ratio of their radii to the intrinsic dimension. And this holds precisely at the limit as these two distances tend to 0. So that means that the knowledge of the local ID allows a conversion between distances and probabilities. If you, asymptotically speaking at least, if you know any 4 of these 5 quantities, you can deduce the 5th one. The first result is just a technical lemma, which I'm stating here on this slide, but let me draw your attention to the parts of it that we need. We have two functions, which are assumed to take value 0 at 0, and thereafter, in the vicinity of 0, they're assumed to grow positively, and that we also assume that their ID values exist, that their intrinsic dimensionalities exist. Then we ask ourselves, what is the limit of the ratio of these two functions as u tends to 0? And so we call this limit lambda. So then, if lambda exists and is positive, not 0, but it exists and is strictly positive, then the ID of function beta must be the same as the ID of function alpha, is the result. And alternatively, if the limit exists but is not positive, then we can ask ourselves whether we can pull out some factors of u in order that the result can be have a limit that does exist and is positive. So from beta, we're going to pull out a number of factors of u equal to the difference between the intrinsic dimensionalities. And then the result we'll call beta 0, beta sub 0. And then we look at its limit, and we look at whether this alpha 0, its limit, and look at its properties. So if that limit exists and is positive, if by pulling out factors of u equal to the difference in their intrinsic dimensionalities allows the limit to be positive, then we can say something about the original limit between beta and alpha itself. So if it's equal, of course, then that happens if and only if the original limit is positive. But if it's 0, we know that the ID of alpha has to be less than ID of beta, and if the original limit was infinite, then the ID of alpha has to be greater than that of beta. So just as a partial proof of the first statement, it follows very easily from the ID formula. So if we consider that lambda exists, if we assume that it exists and is positive, then due to the assumptions on alpha and beta and the IDs, we can apply L'Hopital's rule to the limit, differentiating top and bottom. We can basically show that lambda is equal to the ratio of the IDs times lambda itself. Now, since lambda is positive, then we can divide through by the lambda, and then that we get that the ratio of these two IDs is equal to 1. That means they're identical. If, then, density ratios are only meaningful when the LIDs are identical, well, this is not surprising because this behavior is the same as for ratios of probability densities in the traditional way. However, this way of looking at things retains the advantage that we haven't imposed an arbitrary, universally fixed dimensionality on the model. The next result basically allows us to go back to the ID representation theorem and to look at that factor g of f that sits there, which disappears asymptotically, and then see whether or not in our formulation we need to carry this thing. What this result essentially says is that if you have the limit of the ratio of two functions taken to some power c, which is not 0, times this auxiliary factor from the EVT analysis, g of f, that this factor, that you get the same limit, okay, as if that factor were gone, as long as the limit of the two functions itself, beta over alpha, as u tends towards 0, as long as that's positive. If that's positive, then the GF will just disappear, which is very convenient because that means we don't need to carry around this messy formalism from the original ID representation theorem. It divides out or it disappears whenever we're considering ratios of densities. So if it turns out that C, if it's positive, or depending on whether C is positive or negative, and depending on whether this limit beta over alpha diverges or vanishes, then we can say that the overall limit will either diverge or vanish depending on the cases shown at the bottom here. Then summarizing, whenever the limit exists, then we can drop the G. Then we can formulate a simplified asymptotic version of the ID representation theorem where we parameterize the ball radii in terms of U, and so for example, alpha U is considered to be the inner ball radius and beta U is the outer ball radius, and we get the following result. So basically we assume that F, alpha, and beta are non-decreasing functions starting at 0, and that the alpha and the beta are continuously differentiable, strictly monotone, near 0. Then this just says that if we take the limits of what we saw in the ID representation theorem, that the limit of the ratio of F of these things, that just gives us beta, the limit of beta over alpha, taken to the power of the intrinsic dimension itself. Whenever the limit lambda exists, then this relationship holds. You get the limit of the density ratio to the power of the intrinsic dimensionality. And as the final result, we consider the situation where alpha and beta are invertible. So then, if the density ratio limit exists, then what we have is that it is also equal to the reciprocal ratio of the functions, that is, alpha inverse over beta inverse, all taken to the intrinsic dimensionality of alpha, or alternatively to the intrinsic dimensionality of beta, and that the limits both diverge whenever alpha itself diverges. Okay, so this has an important implication in practice for certain types of density estimation. So in this interpretation, we can imagine rewriting this with functions f1 and f2 as the probability captured within balls of radius r, and look at their inverses, f inverse 1p and f inverse 2p, as those would give us back the radii of balls that capture the given probability p. So that means in a K&N method that if we have p equals the k nearest neighbor value as determined by the ratio of k, our neighborhood size, over n, our sample size, and we take that as a probability value p, then the inverse of f on p just gives us a radius at which that probability would be exactly obtained in a distributional sense. And so that means if we take k nearest neighborhood and take its distance to the boundary, then what we get is an estimate of the distance value r that would achieve a probability of k over n. So that means that in methods such as LOF outlier detection, which use density ratios in their formulations, they use density ratios in the form of an inverse distance in a simplified form. This result essentially shows that the LID should also be taken into account, that there is a modeling error that comes with using inverse distance as a direct proxy. Okay, then to conclude, in this paper we've seen that the limits of neighborhood-based density ratios are more flexibly defined than traditional density ratios, and they naturally account for variations in LID. In working with them, the intrinsic dimensionalities pop up where needed. This use of neighborhood-based density ratios in their limits reveals deficiencies in the use of inverse distance as a proxy for density, and that there are many potential applications that use existing density ratio methods, including in outlier detection, clustering, divergence modeling, and the like, could benefit from this. So thank you very much, and I'm looking to meeting and discussing with you later on in the conference.